Limits at infinity for rational functions. So polynomial divided by polynomial. We took this example. Right, this is one we did yesterday. We found when we did the algebra that we got an answer of the limit is 0, right? Okay, here's my first question to you. Does it matter which direction we approached infinity from? Dangling participle. From which direction we approached infinity? Correct myself. Okay. What do you think? When we plug the infinities in here, would it have made any difference in this problem? No, right? When we plug the infinities in and we got all these terms with x's on the bottom that went to 0, that's insensitive to the sign of the infinity. It doesn't make any difference, right? A really big positive or negative number on the bottom still makes the fraction go to 0, right? So we could have put out in front here, if we wanted to, we could have put a plus or minus infinity. Got the same answer, right? Okay, next example. Okay, let's see if you remember what our technique was. Lily White had a good suggestion. We changed it very slightly. Do you remember what we do here if we want to resolve this indeterminacy? Because if I plug in infinities, I get infinity over infinity, right? So I'm going to factor out what?
X squared.
An x squared, right? The biggest power of x. We'll factor out of each, right? So we'll write this as the limit of x squared times what on the top? Good. And x squared times yeah, this is different than the last one we did. Right. The last one we did the same thing though, didn't we? We factored out an x squared. We just got different, slightly different results.
I think it's like one
The only thing that's the 2x squared.
Either that one.
No, that was the one.
Oh, how about
I'm
that?
so confused right
That's so bizarre that it ends up being the same. It's totally random, but it ends up being the same, almost the same.
now. Okay.
Okay, you see the difference, Kurt?
Whoa, wow.
Yeah, I apologize.
It's been a while.
Different problem. So then as x approaches, now I'm going to go ahead and make this a plus or minus again. You'll see why. The x squareds cancel algebraically. That removes the indeterminacy now. No longer do I get infinity over infinity, but when I take my limit, what happens?
You get 2 plus infinity,
No,
2 plus 0,
2 plus 0,
over 3 plus 0.
which is equal to 2/3. Okay, right?
So why does the whole thing cancel?
Say it again.
Why does that whole thing cancel? Why does it just cancel?
Well, because 2 plus 0 is just 2,
Well,
right?
I know, but why is the 5, why does the 5?
Okay, because if I'm taking a limit of 5 over x squared, as x goes to infinity, think what that fraction's going to do. I'm going to get 5 over infinity, which is 0, right? 5 divided by a huge number becomes small,
Oh, okay.
okay? And once again, when I say 5 divided by infinity, that's hokey. You can't do that, but understand what I mean. I mean 5 divided by a number that's increasing without bound. Just a huge number, right? Okay, let's look at this one. Same kind of thing, right? Okay, what's the algebra going to look like this time?
After x cubed.
Factor out x cubed. On the top, I get
2.
okay.
Plus 5 over x cubed.
Okay. Divided by
3 over x. Plus 1 over x cubed.
okay, and this time, what happens?
0.
Okay, this time we get 0. Right?
But it's not actually 0, is
It's not actually 0, but as x approaches infinity, and let's go ahead and say positive infinity this
it? I
time.
get something. zero, right?
Okay, but, talk to me about that.
Well, I get that it's getting close to it, but it wouldn't actually be that, would it?
No, you're right. So let's do this.
Substitute that.
So you're talking about like this part right here, right?
Yeah.
Okay, so
Like,
let's,
It gets super close, but that has no effect on the overall answer.
it does, but we're taking a limit, right? So here's how you gotta think about this. So you're thinking, well, what if it's like 3 over a billion is still a number, right? Okay, but we're not stopping at a billion. So say a billion squared. 3 over a billion squared is really small, but still a number, right? Well, make it a billion to a billion, right? There's no limit to how far we can go. So no matter where you decide you're gonna stop and say, okay, that's still a number, I get to go infinitely further than that, right? And so this number on the bottom is gonna keep getting closer and closer and closer to zero, arbitrarily close to zero. As it gets arbitrarily close to zero, what's gonna happen to this thing as a whole? Right, I'm gonna end up with a 2 and then a bunch of zeros, right? So I get the answer 2 over 0, which is what?
But if those aren't actually zero, you divide it, 2 by it, that wouldn't be the actual number.
You would, okay, so you would, but like if I say, we want to know what is the limit of this approaching? So let's pick a huge number for x. I could pick a billion. I could plug it in and see what I get. I'm not going to get a super large number, right? But the tendency is this thing's never going to stop increasing, and so in the limit, right, we never get there. You can never get to infinity. But in the limit, as x approaches infinity, this function is approaching infinity. To say anything else would be to indicate that it's going to level off at some point and approach a value, right? But there is no value it ever approaches. It just keeps getting bigger and bigger without bound. The only way to describe that is to say it approaches infinity, or it goes to infinity. Does that make sense?
Yeah.
Okay? Yes, sir.
This one has a diagonal asymptote, doesn't it?
It does. It does. And we'll come back and talk more specifically about why it's a slant asymptote later. I don't want to get into that at this very moment. For now, we're just going to say that the answer is it's unbounded, but we could at least be a little bit more specific about how it's unbounded, right? And this is where I want to talk about something. How do you know on the bottom it makes a difference if I'm dividing by 0 plus or 0 minus, doesn't it? Right? Everybody with me on that? Okay, it makes a difference because if I'm dividing by 0 minus, goes to negative infinity. If I divide by 0 plus, it goes to positive infinity, and those are big time different, right? How do we know? Well, on the bottom, as x approaches positive infinity, that's going to give me 3 over a very large positive number, which is going to give me an overall positive sign, right? But you might be thinking, well, what about this one? And you'd be right to think that. This one's also going to give me this time 0 plus, but what if it didn't? What if that were a minus sign, let's say? What is 0 plus minus 0 plus? Indeterminate, right? How do we know which one to use? Okay, this is where you got to really pay attention because this is a big time concept. We have to leave this discussion for just a second. I've built this cool graph. I may have done this with you at some point in the past, like in Algebra 2. I can't remember if I did or not. Might have. Jury's still out on that.
This is the one where when zoomed in, if here's x, y equals x, when you zoom out of there, here's x squared.
It is. It is. So let's go through this one again. So if I take this function, everybody with me? If I take this function, this polynomial, 0.00 blah 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 1 x to the 4th plus a slightly larger number times x cubed plus a slightly larger number times x squared, etc. The scale at which we're looking at this has a huge impact on what it looks like, right? So if I'm zoomed way in, it looks very much like the function y equals x. These other terms are insignificant, right? But as I zoom out, pretty quickly, it's going to recede from that, right? And now it starts to look nonlinear. Agreed? So let's turn that guy off and let's turn on the next term, 0.1x squared. Those start to look pretty similar as I zoom out, don't they? Right? To a point, right? I gave it away there. But they're starting to look, you might be thinking, okay, yeah, that seems to be the term now that's dominating the behavior. But not for long, because as we zoom out further, it starts to look more cubic, right? At this point, I'm starting to get too shrunken up on the horizontal axis. So let me do something like this. How about, what's that about? 100 and... starting to look pretty cubic, right? Oh, not anymore. Now it's starting to look much more quartic, right? If I keep on panning out, and I've got to compress this thing, or I got to stretch it out horizontally again, so it's easier to see. Now you can start to see that ultimately the final end behavior, you can't even see that other junk in there anymore, can you? Right? Right, it starts to be oops. Right. Now, I mean, can you even see that other little bumps in there? Can you even see the cubic part of the... No. Right? At this point, even if I turn the purple one off, doesn't that look like pretty symmetrical, pretty much like a quartic function? So what that tells us is that the end behavior of a function, right? We don't care about the local behavior, but when you start to approach positive and negative infinity and you get far out on the function, for a polynomial, the only part that matters is the leading term. Right? So if we go back then and we look at our function here, the function on the top and the function on the bottom, we canceled the x cubes, right? So now we've got the limit of 2 plus 5 over x cubed divided by 3 over x plus 1 over x cubed as x approaches, let's say, positive infinity. All we got to do is just look at that part, right? That's the only part that's going to matter, right? Those are the parts. That's the dominant. That's the dominant term on the top function. That's the dominant term on the bottom function, because those are the highest powers of x. Okay. Did we even have to do all this stuff? No. We're going to come up with a simple rule for dealing with these rational functions. We could have probably just done this, couldn't we? We could have ignored all that junk and just looked at those. Right? The ratios of the leading coefficients gave us 2x cubed over 3x squared, which simplifies to, what's that going to simplify to? Simplifies to 2x over 3, right? Does that make sense? Like we could have just reduced that and said this whole thing is just equivalent to the limit of 2x over 3 as x approaches infinity. Or if we want to, we could divide top and bottom by x and make it the limit of 2 over 3 over x. Doesn't matter. I'm going to get the same answer either way, aren't I? If I let this thing go to positive infinity, I'm getting a positive coefficient times infinity. Right? See what I'm saying? Okay? So that's a positive sum. What if I made this negative, and what if I approach negative infinity? Well, I'd get negative infinity for my answer. So I can be more specific with it, right? I know, now let's break this down into, tell me what the patterns are. Okay, so the patterns are, if I have a rational function, what's different about this one than the other two examples?
The terms on the bottom.
Well, they both have leading terms, but what's different about the polynomials?
The highest power polynomial.
Okay, so the larger polynomial is on the bottom, the one with the higher degree, right? What did we get for an answer? 0, when we took the limit as x approached plus or minus infinity. We can generalize that, right? Anytime you have a rational function where the bottom is a higher degree polynomial than the top, you know that the end behavior is the limits go to 0, right? So you're going to get a horizontal asymptote on the x-axis, essentially. You know what that's saying? If we take the limit of this function as x goes to positive infinity or negative infinity, and the value of the function goes to 0, that's just a horizontal asymptote of 0, right? Okay, what's our recipe for this one? This just generalizes where the degrees are the same, top and bottom. So somebody raise a hand here and somebody tell me what's going on. What's happening with this one? Our result is 2/3. Where do we see the 2/3 immediately? Leading coefficients, right? We just look at the ratios of the leading coefficients. If the degrees of the polynomials on the top and bottom are equal, you get a horizontal asymptote at y equals the ratio of the leading coefficients. Like the limits go to that value. If the polynomial on the top dominates, do you get a horizontal asymptote? No, you don't. Right? Then the function does blow up in the tails. Right? And we could be more specific and even say, well, in what directions, is it going up or down, right? Going to positive infinity as we approach infinity, or is it going to negative infinity as we go to the right? When I say approach positive infinity, what I mean is we go to the right forever in the xy plane. Is it doing that or is it doing that? Right? We can tell just by looking at the ratio of the leading terms and puzzling out what the sign's going to be. Okay? So there's a little summary. What we just said. Okay, and we'll get more specific with number 3, just not at this very second. Okay? Okay, so,
Wait,
we're back. Okay, I'll go back.
And so both limits are true whether it's going from to positive infinity and to negative infinity.
Yes. Yeah, so these are, you're getting one shared, and we'll come back and talk more about this when we focus on curve sketching. We'll review this later in the year. What we're going to see is, yes, the skeleton for this function is going to be at the end behavior. For 1 and 2, you get this shared horizontal asymptote that both ends are going to stick to. Okay, it doesn't matter if you're going positive or negative. In the positive or negative direction infinitely far, you end up on the same asymptote. Okay? Okay, so we good with that? Yeah, I'm just going to, I'll remind you about something too. See a lot of people taking pictures, and that's fine. I don't have any problem with that. But just so you're aware, let me remind you that you can easily get to this if you go to instructional notes. There's everything we've done. There's yesterday right there. If I click on that, there's everything we did yesterday in class. Okay? Okay, so what about this then? Just quickly. I guess I want to know, is there going to be an answer, or is there going to be no limit? Does not exist. Okay, right. We're going to have, and if we wanted to be more specific while we're at it here, let's just call this f of x. The limit of f of x as x approaches positive infinity would be what? I know I'm getting infinite, right? Because the top is bigger order than the bottom, so it's blowing up. So I know I'm getting infinity. What's the sign going to be? Well, all you got to do is look here, right? Look at the leading terms. What's the sign of that factor on the top going to be? If x is positive, 3x cubed is positive. X is positive over positive is? There you go. Okay? Make sense? Okay. Okay, we just did one like that. Okay, let's do this one. I'm going to be, let's say the limit as x approaches negative infinity. What can you tell me about it? First thing probably is what? Do we get a horizontal asymptote? No. Blows up, right? What's the sign going to be? As x approaches negative infinity, what's the sign of the leading term on top going to be? Positive, because a negative number squared times 5 is positive. Everybody see that? So I'm getting positive. On the bottom, I'm going to get negative, right? Because I'm approaching a negative number. Positive times negative is negative. Positive over negative is negative. Okay? Make sense? Okay?
So I thought if the degree on the numerator was bigger than
Say it again.
is that if the degree on the numerator was bigger than the denominator?
So, okay, so there's two parts to this. What does it mean? What does it mean that the top is a second degree polynomial and the bottom is a first degree? What's that telling us? Infinity, right? That tells us infinity.
So if it's just one, it's a zero.
Well, that tells us if the top polynomial is a stronger polynomial that has a higher degree than the bottom, then you know it's blowing up, right? But we just want to know, let's look at the ratio of the leading terms to see what's the sign going to be. Is it doing that or is it doing that to the right? Yes?
Doesn't matter how much bigger the top is.
It does. It impacts the shape. It does. And we'll come back to this. It's a very good question.
For this, it doesn't
No,
though.
not for the, no, not in this case, not when we're just trying to see if it's positive or negative, right? So if this were, hypothetically, what if that were a cube? Then we would have gotten a negative number cubed is negative times 5. That would have been negative over negative, so it would have been positive then, right? But it actually does have an impact on the shape also. Okay. And you might be thinking, and you'd be right to kind of wonder about this. Even from the beginning, maybe you could have reasoned out that this thing's going to explode. The fact that the top is going to infinity and the bottom is going to infinity seems like they ought to cancel out, but the top is going to infinity infinitely faster than the bottom, right? So it dominates. That's why the whole thing explodes. Okay? All right, what about, okay, that's where I left off. Okay, so now I want to, what else did I have planned here? I had some other goodies up here I wanted to show you. Where are these guys? Right there. Okay, which one's this? So here, might as well look at this. So here's a graphical demonstration of what I just showed you, right? So look at the top one, right? If we zoom out on this thing, can you see that this asymptote is going to 0, left and right? If I graph the line y equals 0, let's make that different color. Whoops. Everybody see that black line down there is the asymptote for that function? Sure. You like that color?
Well, I mean, there's like the line.
Yeah, that's a pretty bad color. I agree. That's pretty bad. Let's go purple.
Oh, yeah.
There you go. Make sense? Okay. So how about this one then? If we turn that guy off, let's go down here. What if we pick a function where the top and the bottom are the same degree polynomials? Then we just take the ratio of the leading coefficients, right? So now my horizontal asymptote is at y equals 2/3, right? And if we pick one where the top is higher degree than the bottom, there it is, right? Okay, make sense? Well, because that's the local behavior. Close to home, it kind of close to the origin in there, it does weird stuff. But on the large scale, what we're going to see is this is a slant asymptote. If you zoom way out, the asymptote dominates the behavior of the function, just like it would for any of these. If I go up to this guy, right? Oh, oops, it is. I meant this one. Right, so it does weird stuff locally, but when I zoom out, eventually it just looks like a line, right? Okay.
So with the slant asymptote for the following, the y equals 2 is x.
No, I'll talk about how to get slant asymptotes pretty soon. Here's another one, right? Locally, it does weird stuff. It's got a vertical asymptote of -1/2, doesn't it? Right? If I graph the function, or x equals -1/2. Right? There's an asymptote. Bad color. Oh, Emily's going to want purple, so I'll do purple. Right? So there's the local behavior. You get this asymptote. But if I zoom out, look what happens. It just looks like it's going to be just an asymptote. Okay? All right. We'll come back to that one again. Okay, so what about, though, there's some other kinds of problems we got to deal with. So we got these rational functions. What about something like, let's say, how about this? What if I did f of x equals, let's do 2x minus sine of x squared divided by x. What do you think about that one? That's supposed to say limit. Yeah, it's like that. That's kind of a fast kind of mind of its own. So what's going on with that? So this isn't a polynomial on top, is it? Right? It's not a polynomial, but we can still think of it like that. Think about the two terms in that expression on the top. What can you tell me about sine of who cares? Yeah, it's trapped, right? The output of that function is trapped between -1 and 1, so that's insignificant, right? This one, if I approach infinity, that term is going to change, is going to explode. This term stays trapped. It's never going to settle on an individual value, but it just recedes into the background noise. It's such a small little wiggle, isn't it? Right? So the dominant term of the top is clearly this one. Right? Everybody see that? And so I can think about this the same as I did before. The limit of f of x, so this is true. The limit, I'll write this function down, of 2x minus sine of x squared over x, as x approaches plus or minus infinity, is exactly equal to the limit of 2x over x, isn't it? That's going to become vanishingly small in comparison. And what's the limit? What's that limit equal to? So, right? Okay. How about this one? You have 5 minutes? What's that? 4. Oh, okay. So let's do the limit of.
Something with that.
So here's where we'll leave off for today, and where we'll maybe pick it up tomorrow. Okay, what about this one? Let's just talk about our thinking on this one, because there's a way we can finesse our way around this. If we just think about this, which is a good thing to do, right? So if we approach positive infinity, is there a dominant term on the top? 2x, right? That's the leading term in that polynomial is going to dominate. Okay, now let's look at the polynomial inside the radical, right? Because we can isolate the behavior inside of the radical. We can focus on that. This is a composition of functions. We have a square root of a polynomial, right? So what's the dominant term of the polynomial? On the bottom? X squared, right? So if that's the dominant term and we can ignore the other ones, then you see that this limit is exactly equal to the limit of 2x over the square root of x squared. Right? Do you see that? What is the square root of x squared?
Absolute value of x.
Absolute value of x. Right? So this looks like the limit of 2x over the absolute value of x, right? As x approaches infinity, and we can even isolate this behavior then, right? We've talked about that before in here already this year. Do you remember if I take the function, let's call it g of x, if g of x equals x divided by the absolute value of x, if we write that as a piecewise function, it's pretty boring. When x is positive, what is that?
Positive.
1. Good, because I'm going to get x over x, right? When x is less than 0, it's negative 1. And when x is equal to 0, of course, it's 0. Actually, it's undefined.
Yeah.
Undefined. Can't equal that, can it? Oops. Okay, so then we're just multiplying 2 by this piecewise function. So whenever we see either an absolute value of x over x or its reciprocal, that's a graph you always want to be thinking of this, right? If you're thinking of this graph, we drew this earlier. It's just this graph. Right? And so all we're doing is multiplying 2 by that graph, so it's just stretching it up by 2. That's our answer. Right? So the limit as x goes to positive infinity would be 2. Right? Okay. Without even thinking about what that graph looks like, you could just evaluate this using your sign conventions too, though, couldn't you? Right? You'd know that x over the absolute value of x, those have the same strength, right? So they go to 1, but if I play the sign game, I'm going to get positive over positive times 2 is positive 2. Right? Does that make sense? Okay.
Hey, if you didn't get a cupcake, please take one. I'm not trying to hit you.
Oh, a cupcake? You have to ask Mr. Oya twice if he wants a cupcake.
That's
What?
what.
So the problem that I had on Google for the